Welcome to the 16th lecture video for Physics 4A. Having covered everything we can consider when we treat objects as point masses, in this lecture, we are going to start considering dynamics of an extended object, sometimes called rigid body. In some sense, in this and the next few lecture sets covering rotation, we don't introduce anything new. No new laws of physics, and no new principles. But the tools we introduce will help you build mathematical models of the real world more accurately and realistically. We start by introducing torque through consideration of a couple static equilibrium scenarios. This is not the typical order in which rotation topics are covered, but I want you to emphasize and demonstrate that having covered everything we covered through lecture 15, we can figure out rotation through the things we already know. The static equilibrium scenarios allow us to introduce torque with as few assumptions as possible. And having introduced the torque, we will be able to use this tool in the next lecture to come up with the correct expressions for other rotational quantities, such as rotational inertia. Since we introduced the torque through considering a static equilibrium scenario, we also use it here to analyze a couple interesting static equilibrium scenarios, highlighting the additional things we need to consider as we work out the dynamics of rigid bodies. And in drawing FBD of a rigid body, you will see some conventions we take when it comes to considering contact forces that act over a surface, like the normal force. We wrap up this lecture with the introduction of rotational kinematics, introducing the language we will need, for example, angular velocity and angular acceleration, as we start rotational dynamics in the next lecture. One thing I want you to pay attention to here and in the next lecture is analogies. The analogy between translational quantities and the rotational quantities will both help you remember the formulas you need to memorize and help you develop a sense of intuition for rotation, leaning on your existing sense of intuition for translational motion, that is, what we have been calling just motion.
Okay, so we are starting something new today. In some sense, it's not completely new. It's dealing with a situation that you have seen before. So if I have an object sitting here, this is what we call equilibrium, or even static equilibrium. So the idea of equilibrium is simple. I think I might have used that word a few times, but I probably didn't properly define it. Have I defined the word equilibrium? Have you people here have heard the word equilibrium? What do you think equilibrium means? If you just heard it, just out of blue, somebody talks about equilibrium. Right? Steven?
So like, if you don't do anything to like a system, it'll just stay that way?
Yeah.
But if you do something,
Yeah, it'll maybe move away from that. But the idea of equilibrium is that it's the situation where things are somehow equal. It's sort of going to remain that way. So let me define equilibrium using the mechanical concepts that we've introduced. So we would define equilibrium as saying, all right, net force is equal to 0. Is it, I don't know, clear why we would define equilibrium this way? I guess starting from why we would use even force to define equilibrium. Like what's special about net force being equal to 0?
zero acceleration.
Zero acceleration, that's what everyone's thinking, right? Yeah, so when net force is equal to 0, that means your acceleration is equal to 0. And so that's what we're talking about when we say equilibrium in physics. Equilibrium is a position where acceleration is 0. One last example of equilibrium that you have actually seen, I might even have said the word equilibrium, but didn't didn't go into too much detail, is the equilibrium with respect to the mass and the spring system. So I think I'm pretty sure I've done this at least once. Label this position, call this X equilibrium. Like this is the equilibrium position. And when we say that, now the way I can describe that now is that, well, that's the position where net force is 0, so the acceleration is 0. Now, if I pull this down, I don't call this equilibrium, because right now the net force is 0 because I'm holding on to it. But when I imagine me not holding on to it anymore, acceleration won't be 0. So even though it's at, I guess this is the clearest example where velocity equal to 0 doesn't mean equilibrium. At the very top and bottom, its velocity is 0, but that's not an equilibrium because this is how we define it. So static equilibrium is where, in addition to the definition of equilibrium, you also have velocity equal to 0 in whatever reference frame you are measuring velocity. So this, for example, is in static equilibrium. Good? Yes? Now, it's clear that this acceleration of this block is 0, right? Okay, so that's a static equilibrium. Now, when you start looking at more situations that involve static equilibrium, as in things are, so with the static equilibrium, because your velocity is 0 and acceleration is 0, things are at rest, velocity equal to 0, and they will stay at rest, acceleration, because velocity, that 0 velocity won't change. So as you look at more situations that involve static equilibrium, you will soon realize that this condition here is it's insufficient. Let me give you an example where you can see that something that's at rest, even though the net force on it might be 0, it's not staying at rest. So I have a ruler. Let me put this here. All right. It's at rest. It's staying at rest, right? Okay. Let me push it over a little bit. Actually, let me push it over this way. All right. Okay. So somewhere around here. So when this ruler is positioned like this, and when I let go of my hand, do you believe that the net force on this ruler is still 0? Close to 0, right? And if you want to make absolutely sure it's 0, I can even put it on my hand and make sure I push it up with enough force that net force is either 0 or upward. Okay? But what else do you see going on with this ruler? It's rotating, right? That's what you're seeing here. So up until around this point or so, the net force on the ruler was 0. And there was something else pertaining to the ruler that was 0. We just weren't recognizing it because up until this point, we haven't dealt with the rotation. We only dealt with the linear motion. We only dealt with things like acceleration and combined with the position and velocity. And these things are the things that describe translational motion or linear motion. What we mean by translational or linear, it's clear, right? I don't have to go into explaining what those words mean. Yes? Yeah, things just moving in a line. Now, we have seen circular motion where things are not moving in a straight line, but things are going in a circle. We have seen that. But even that, we kind of described it like a translational motion. Because we are talking about, all right, this mass here is moving with some speed in this direction. And because of acceleration, its direction is changing. And we are looking at it as a linear motion. We are not quite handling as what we are going to do now, rotation. So this is the first time I'm pointing out that translation isn't the only motion you can have. You can also have rotation. And that's what you're seeing here. As I push this over, even up to about this position here, net force is still very close to 0. And even here, net force is still very close to 0. But as you are beginning to see something happening to the ruler, something else is not quite 0 anymore. Move it a little bit more. And even though net force is 0, as in you are not seeing this ruler dramatically accelerate downward, something else is not 0. There's a whole set of quantities that we are going to look at that will cause the second type of motion. And the second type of motion, it looks like it's rotating, right? So we're going to call that. In fact, we will call this rigid body rotation. Rigid body rotation is what we want to introduce today. That when you have an extended object, like this ruler here, then for me to try to specify that it's going to stay at rest, it's at rest and stay at rest, it's not enough for me to say that net force is equal to 0. I have to say something else is also equal to 0. Because when I try to support it here and let go, even though I'm going to provide as much force as possible from my finger, there's no way I can keep this at rest. I have to somehow put this at the exact right position to keep it at, make it stay at rest. Somehow, if I'm applying force at the wrong position, there's nothing I can do to keep this at rest short of moving my hand over. Yeah? So this quantity that we are going to associate with rotation, we are going to call it torque. It's a new word. I mean, you might have heard the torque in other contexts before, but I want you to treat it like a new word. We are defining torque for the first time in this class. So, do you guys remember how we defined the force? I mean, we eventually said force is mass times acceleration. But what's the one property of force? Arjun. Changes the position of the body. Okay, so some kind of motion, right? I want you to be careful. So right now, is the position of this body changing? Yes, right? Is there a force until I call it here? I mean, if you ignore friction, no, right? So, okay, so it does have something to do with the motion. So you could almost say force causes motion, but I want to be careful with how I describe that motion. What does force cause? Acceleration. That's how we describe the force. So we started out this class with the study of motion, right? Position, velocity, and acceleration. And we spent the whole class doing this. Force doesn't cause the velocity. Like force is not necessary to maintain velocity. But what force is necessary for is for changing velocity, which will be related to the acceleration, right? So we are going to develop our language and intuition for rotation the same way. So when we talk about torque, I want you to have this in the back of your head, that everything I'm describing with the torque, the intuition for that is going to come from force. So that's why I'm going over what we already talked about with the force. That force causes acceleration. So with the force, you could say, force causes motion, where you clarify what kind of motion you mean. You mean, by motion, I mean acceleration. I don't mean velocity, because that was the mistake that ancient Greek philosophers are making for thousands of years until Galileo and Newton straightened them up. So with the torque, we are going to say something similar. So we'll say torque. Well, I want to model after this. So we'll say torque causes rotation. And I want to be a little bit careful about what I mean by rotation. This is a bicycle wheel. It's something that can rotate, which is why it's great for this demo. And so right now, as I'm holding this bicycle wheel, is it rotating? Okay. Does it look like I'm trying to make it rotate? No, right? I'm just holding onto the axle. I'm doing the same thing I'm doing here right now. So when we say torque causes rotation, we don't mean that when something is rotating like this, that there must be torque on it. So how do we want to clarify what we mean by rotation here? What we mean by quote-unquote rotation, what would you say, what is the kinematical quantity that you would say torque is causing? Asia? Changes in rotation. So I think the word rotation, it has the same problem with the word motion. It's that they are ambiguous. When I say rotation, what do you mean? Am I talking about how fast it's moving? Or so Asia suggested changes rotation. Let me suggest a little edit here. So I'm trying to move away from the word, just using the word rotation by itself, because it's a bit of an ambiguous word. The same way motion is an ambiguous word. So I want to say it changes how fast something is rotating. Good? So as in, when I'm holding this still like this, how fast is it rotating? 0, whatever it is, 0. And I'm not trying to cause it to, I'm not trying to apply torque, it seems. So it's not changing from that 0. Now, if it's already rotating, I'm still not trying to cause any torque on it. So it seems to rotate at whatever speed it's already rotating, right? So the intuition we associate with the torque is what I apply when I'm trying to make it go from 0 to something not 0. Or when I try to make it go from something not 0 to 0 in how fast it's rotating. Good? Yeah, so we are going to introduce all the proper words for describing this, give it the actual proper definition towards the end of today's class. But let me just say, this is what torque does. Torque, it causes rotation, where I want to clarify what I mean by rotation, because once again, it's an ambiguous word. And I'm going to call what the torque causes as angular acceleration. And we'll define angular acceleration more carefully in a little bit. But I hope you notice some similarity with our intuition for force. Force is what causes acceleration, and you're familiar with how all of that is defined. And what torque causes, we are going to also call it some kind of acceleration. It's an angular acceleration. So that's what torque causes. I found it more easy to try to define torque using situations where net torque is equal to 0. Because those situations are easier to identify. Those are the situations where I see something that's not rotating, and I can say, hey, maybe it's not rotating because of this and that. Or, I can take this situation and start messing with it, start changing some things, and then I see that, oh, now it rotates. And then I can try to figure out, okay, why is it now rotating? Yeah? Because, I want to tell you this. With everything we have covered through Tuesday, we actually have covered all the laws of physics you are going to see, all the fundamental laws of physics you are going to see in this class ever. So this whole rigid body rotation, I'm not actually telling you anything that you don't already know technically. I'm introducing new tools for describing some of the most unintuitive motion you are going to see this week and next week. So all I'm introducing is just some add-on to something that you already have. So that's why I want to derive torque from the sense of intuition that you already have from the description of force and all the translational motion. And I found that it's easiest to do it if I use the static equilibrium as the situation to introduce some intuition about torque and use that. Okay, so let's look at a few, one situation. So there are actually, it's these situations that labeled here, and I've been doing meter stick stuff already. Let's actually look at example A a little bit more detail. This is the situation that I'm trying to model here. So I guess simulation is already running. So this is the seesaw. So if I pull this down a little bit, you see it's It can teeter back and forth. I don't know. I was playing with it, and it's not very stable seesaw. Good? Very clear? Okay, let me make a few children. Boxes. That's how I see people. Let me actually clone a few more of these people. All right. So when they talk about seesaw, this is what they're talking about. Let me pause the simulation. And if two children are at both ends of the seesaw, what do you expect to see happen when they jump on the seesaw? Balances, right? Okay. Now imagine that the child on this end is twice as heavy. You don't have to imagine, I can make it. Material, all right. Let me make his density twice as much. So his density will be 4 times. Oh, okay, it doesn't balance anymore. All right. Now let me ask you this question. Is there anything I can do with this system to make them balance?
Yeah.
What can I do to? Yeah, I can put them in different positions, right? Let me put a little fix here so that the seesaw doesn't move as I position my children. All right. So I want to put them in a way that the seesaw will balance after I remove that fix. Okay, actually direct center of mass. All right, how do you think I should position? Should I position the lighter child farther away or the heavier child farther away?
Lighter child farther away.
Yeah, you guys all have an intuition for this, right? Lighter child should be, if the lighter child is maybe at the end of the seesaw, then the heavier child would be about how far away? Half of the way, right? I mean, that's the intuition that almost everyone has. All right, let's see if that works. I'm gonna get rid of this fix, and yeah, they kind of balance. Not exactly. All right. So I guess he wasn't quite close enough. Maybe somewhere here. So let's try that now. Yeah, they balance here, and you know that's the intuition you have. And I want to use that intuition to define torque. So torque is this quantity that causes rotation, by which I mean angular acceleration. And this is the situation where there's no rotation. And it's not because there's nothing that would cause rotation. You can see that with the hypothetical. If I remove my heavy child, then it rotates. What direction would you call that? The rotation is just rotated in. So imagine the clock. Counterclockwise is like one that rotates this way. So what that's showing is that this child here is trying to cause counterclockwise rotation. And if I get rid of the lighter child, then it rotates clockwise. So when you look at this system, there are things that are trying to make this thing rotate. As in, the lighter child is trying to cause this to rotate counterclockwise. The heavier child is trying to cause it to rotate clockwise. It's just that in this particular situation, they happen to balance each other. So that the net torque, kind of like a net force, net torque is 0, so they remain at static equilibrium. So how would you define torque? So the point of me saying that we have covered everything you need to know, I should be able to define torque in terms of other things that we know so that we can actually calculate torque if we wanted to. So if I said there's some torque due to lighter child that we can calculate here, what quantities should it depend on? So when you say mass, you really mean weight, right? Because the child with more mass also has more weight. What kind of physical quantity is weight? Weight is a type of force. Yeah. So we think torque should depend on force. Now, it doesn't depend only on force, because here, the force of these two masses are different. So their weights are different, but somehow they are balancing each other out. So this torque must depend on some other things. Position?
From the people.
Yeah. So something related to position, and your intuition says that the kind of position that matters is how far away these two masses are. So I want to say torque depends on force and distance. And if you think about it for a while, especially using this situation, what should your torque look like? I hope this formula makes intuitive sense. If I said that torque, by the way, let me introduce some of the symbols that we are going to use so that I don't have to keep writing out torque. So the symbol that we are going to use to represent torque most of the time is this letter. How many people have seen this letter before? What is it called, Ratana? No. Okay, how many people know what the name of this letter is? RJ? Tau, yeah. This is a Greek letter. It's lowercase tau. Uppercase tau actually looks exactly like uppercase t, so I will never use it. Lowercase tau, it looks nothing like my t. It has a little tail that bends. It also looks nothing like my lowercase t. It doesn't have the top. So Greek lowercase tau is what we use to represent torque for hopefully obvious reasons. And so what we are going to say is the torque is equal to, let me give you a guess at this formula. Say that it's force times distance. And we will refine this a little bit later. But this formula seems reasonable, that torque is force times distance. Yes? That kind of explains this, right? So the force of this heavier child is greater, but because his distance is less, he's not able to push the thing as much as, he's not able to rotate as much, so they balance out. Okay? Let me do a couple more fun things. And in fact, let me look at a bit of a mathematical detail, then you would question this a little bit. So let's say I try to write this down as a formula. Say that torque is equal to force times distance, so some kind of change in position. Wait, that doesn't quite look right. Because I remember that force is a vector, right? And I also remember displacement is a vector. But if I say that, have you seen this before?
Yes, that's a work.
Work, right? So the quantity I'm trying to define is actually not work. It's something different from work. In fact, let's erase this for now. How is torque in particular different from work? What property does torque have that work doesn't?
Rotation.
I mean, yeah, it has something to do with rotation, but maybe work is what you need to get things to rotate.
Angular acceleration.
We are going to relate to angular acceleration, but I mean torque as a mathematical quantity, Stephen.
Should be a vector.
It's a vector. Torque has a direction. As in, if I have this wheel, so I can rotate it in ways where its kinetic energy will increase. So I'm doing positive work both times. But when I spin it this way, I'm spinning it counterclockwise as you guys see it. But if I spin it this way, I'm spinning it clockwise as you guys see it. And in fact, later on we'll see that torque is a full vector quantity. It's not just in one-dimensional one way or the other. It's a three-dimensional vector. So when we look at torque, it has to be a vector quantity. So whatever this is, it cannot be a dot product. Because it's a dot product, you'll get scalar quantity. We can't have that. So for now, I'll leave this blank, and we'll cover that on Tuesday. But this is what I want to describe for now. Because I recognize force and change in position are vectors, that means they can have relative direction between them. Right? So when I look at torque, these are the full list of things that torque will depend on. Torque, the magnitude of torque, so that I don't have to worry about the direction for now. It's going to depend on the magnitude of the force. For now, I'm not going to worry about the force as a full vector quantity yet. Magnitude of displacement, for now. And the third thing that I'll have it depend on is the angle between these two vectors. Yeah, call that theta. So, illustration would be like this. So this is force, this is delta x, then this would be what I'm labeling theta. Okay? And this was also the case with the work. The angle between the two vectors mattered, right? And I have a hunch that with the torque, it might as well. It might also. So, I have some parts of this formula that I can get from my earlier intuitive guess. I can say, all right, it should be the magnitude of force, scalar multiplication, with the magnitude of displacement. Let's see, I have that far. Now what I want to look at is how it depends on this angle. Because if it was, something like cosine theta, then might as well be work. That was work. And we'll see how it, for a torque, even when you just look at the magnitude, it'll be different from work. So let me play with this a little bit. I think that's one of the good things about simulation. Once you have some confidence that this is simulating something that's a reasonable approximation of real world, then we can kind of look at it. Let me do it this way. Instead, I'm going to have a thruster. So here's a thruster, and here's a thruster. And I can actually, so this is some device that is just, all that's doing is it's applying force wherever it's attached. So I'm going to have use these thrusters to apply force in a particular constant direction. And if I make one thruster stronger than the other, twice as strong, then you see that they rotate. Good? All right. So let me make them both 10 newtons. And what I'm going to try to find a way to do is, right now they all balance out. It's like having two equal weight child, one of 1 kilogram, the other one of 1 kilogram there. And what I'm going to try to do is, is there something I can do to these thrusters to make this rotate without changing the magnitude of the force? So without changing the magnitude of the force or the magnitude of displacement. I can try changing the angle of the thrust. Let's give it a try. Let me fix it down so that it doesn't move while I'm doing that adjustment. And I guess I will make this angle a little bit like this way, 45 degrees. So one way to look at it would be, so this is the displacement here. So this is my vector delta x. And this is my vector f. And guess it depends on how you label your angle. You could be either labeling this angle here as theta or this angle here as theta. But whichever, that's the angle, right? Before, they are both at 90 degrees. Now, one is still at 90 degrees, the other one is not. Which direction do you expect the seesaw to rotate in? Clockwise or counterclockwise? When you say clockwise. Yeah. So that's the intuition that you already have. It's an intuition that you have from everyday experience before you knew any formulas. And when I remove this pivot, you will see that, yeah, your intuition is right. It does rotate clockwise. So what I want to do is I want to guess at a formula that agrees with that intuition. So if I say it's a cosine theta, that's not right, because cosine of 90 degrees is 0. So when this became no longer 90 degrees, torque should have been greater counterclockwise, but that wasn't. So what other expression here will actually work? Sine theta? Yeah, I mean, that's the other choice, right? It's either that or just multiply it by theta. So, so I will say, guess, all right, so f times delta x times sine theta. And let's see if that's true. So, so here's one way I can sort of see if the sine theta is true. So let me get rid of my rocket. So let me make the force kind of much smaller because, wait, let me, material, okay, infinite friction, that's good. So yeah, with this right now, even at this angle, when I get rid of this pivot, then it'll make it rotate, right? So if we are right about this being sine theta, at what angle can I put the force relative to the displacement so that it'll apply zero torque? 0 degrees, okay. So wait, which way is this 0 degrees or is this 0 degrees? Should it point to the right or left? To the right, really? Everyone thinks, once again, this is my delta x. So for the force F to be at 0 degrees, should it point to the right or left? Left, okay. Well, let's try left first, and then maybe we'll try right. So let me rotate this to the left. So, force is pointing in the same direction as delta x. Let's see what happens. It might make it fly. If it does, I'll change some things. Oh, nothing happens. Or maybe it's not running. Okay, never mind. It is running. So yeah, it does make it rotate. It's just that, in fact, you can, that's an accidental. You can see it here. When this comes to this position here, when the rocket aligns with the displacement, it doesn't, so it sort of oscillates about this point because here's the equilibrium position where the torque due to rocket is 0. Okay, so what about the other direction then? What about so if it points this way, okay, so now the force is pointing to the right. So here it's 180 degrees. Based on this formula, what do you expect the torque to be?
0.
Also 0, yeah. So your intuition wasn't incorrect. And in fact, it'll turn out that, but okay, so right now when this is at something small, reasonably small, let's make it 2 newtons. Then at this direction, it provides 0 torque. And when it's rotated this way, for example, now it provides non-zero torque. Yep. Everyone okay? Yes? Yeah. So, so this is the formula for torque. Force times displacement times sine theta. And we'll use this for today and much of tomorrow. We are going to refine this one more time to actually describe what kind of product here is. The symbol we use for the product here is something called a cross product, or it's sometimes called a vector product. Depending on how far you got in math, you might have seen it already. So this is our long introduction to torque. And yeah. And so I want you to show you some situations involving torque that illustrates how you should change some of the things that we have been doing. So, so let me show you a situation that you could analyze before. I mean, we probably wouldn't have because it's kind of trivial, but so this is the setup for the situation that I wanted to demonstrate. It's a ladder leaning on a wall. So, so this, I think I meant this to be my Carpenter. Let me put that over there. This is my ladder. Let me just lean it against the wall. All right, it leans, right? That's a ladder that you have seen. And here's something interesting. So, if we were to analyze this ladder, what you would have done is, all right, there's gravity pulling it down. There's normal force pushing it up. That force is equal to 0. It's at equilibrium, right? And that explains why it's not moving. Now, let me change the situation ever so slightly. I'm going to, pause the simulation for a bit. I'm going to lean the ladder at a slightly different angle. So as in, I haven't changed much. I'm just going to lean it at a slightly different angle. And, let me drop it gently the same way I did it last time and see what happens. This time the ladder slides away. So what made a difference? Why didn't this ladder, when I place this here, this doesn't slide, but the other one does? Any ideas? So there's friction, but when we looked at static friction, this is what we said about static friction, right? That its maximum value is given by the normal force. Between this and the other scenario, do you think static friction changed a lot? I mean, do you think normal force changed a lot? I mean, normal force here, your intuition should say this is, normal force is approximately mg, because normal force is what's balancing out the gravity. And between this position, let me slowly slide it to the other position. Between that and this position, when I let go, the only thing that has changed is the orientation of the ladder. And somehow that made a big enough of a difference that it doesn't slide here. But when I pull this out a little bit and let it go from rest, now it'll slide. So this is a change to the way we have been doing things. So far, if I wanted to analyze this situation, this is what I would have done. I would have drawn free body diagram, and I want to draw it as simple as possible. So I would have said, all right, I represent my ladder with a dot. So I do say, all right, here's the dot, and there's a gravity pulling it down, mg. There's normal force pushing it up. And I would just say, all right, looking at that, you know what? I think a net force is equal to 0. Right? So far, everything looks good. And if you remember my rule about drawing forces on free body diagram, I try not to draw any force that I don't see a need to draw. Right? So here, I see this, well, net force is equal to 0. And my criterion for static equilibrium says net force is equal to 0. I see nothing wrong with it. I'm done. And if that was my approach, then it will greatly puzzle me. When I pull this out a little bit, like should anything in the diagram change?
Yeah.
Like what should I change? Is the weight not mg anymore?
No, you're changing the angle.
I'm changing the angle, but does anything in the diagram represent the angle? Mg is still pointing directly downward, right? And normal force will still point directly upward. But something has changed. Something has changed enough that when I let go, now it slides. So this is going to be a change in way that we do things. So one, I forgot to mention this earlier, that for the static equilibrium condition, in addition to saying net force equal to 0, we are going to say, in addition to that, we also have to say net torque is equal to 0. This seems intuitive enough. Like that's what we are dealing with so far, right? We say net torque is equal to 0. What that means is angular acceleration will also be equal to 0. Yeah. So in this situation, this is how we have to, so now it's because when you look at torque depends on where you are applying the force. So far, we didn't really care where the force was applied. If I have this cart, which is sitting here, then all that mattered for normal force is that it's upward force somewhere on this object. Gravity, all that matters is downward force somewhere on this object. And that's why I represent all my objects with a single dot, because I didn't care where the force was on, as long as it was somewhere on the object. That's going to change now. We now care where on the object that the force is. So what that means is that this diagram doesn't work for my free body diagram anymore. Let me draw my free body diagram. I mean, I'll still try to draw my free body diagram reasonably simple, but this is how I'm going to have to do things. I'm going to have some kind of representation of the object itself. So I'll say, all right, this is going to be my free body diagram. So it still doesn't change the fact that there's gravity acting on this thing. And I'll justify this a little bit later. I'm going to say gravity is at the center of mass. So, I mean, it's not technically true. Force of gravity is spread all over. But mathematically, I'm going to treat it as if all those different forces of gravity, that when I average all their effects, that it's as though they all act at a single point, the center of mass that we've been talking about last time. which is why I had to introduce it. It's acting at the center of mass downward, mg. Okay? So before I was talking about the normal force from the floor. That's why I was pointing upward. Well, where's the normal force here? Like, what's the only point where the normal force can be? The point of contact, right? It's the only point where the normal force can be. So this is where the normal force is. Now, as you look at this diagram, now you should see the question that whose answer to the which is now different. So so this is static equilibrium. So the question that we continue to ask is net force equal to 0, and is net torque equal to 0? This diagram, can net force be equal to 0? Right? Downward, upward, they can balance out. Here's the question. Can net torque be equal to 0? Look at these two forces. Do they look like they are spinning the thing, in two opposite directions, one clockwise, one counterclockwise? Or do they look like they are trying to spin the thing in the same direction? It might be easier if I define some kind of center of rotation, like the point around which it's doing the rotating. Let me give you two different points, or actually three different points, and hopefully the answer to all three will be the same. I can imagine taking this and making it rotate about this point. What direction is gravity trying to make it spin? Is it making it trying to spin at all? No, because here this delta x is equal to 0. So, all right, it's not trying to make it spin at all. Oh, wait, shouldn't erase it. So I'm done with the gravity. What about the normal force? What direction? Not up. With the direction of torque, I want to talk about in terms of counterclockwise and clockwise. Yeah, counterclockwise is going to try to make it rotate counterclockwise. So, all right, so the combination of these two is that they are going to try to make this object spin counterclockwise. But, maybe you don't agree with my choice of where the center of rotation is. Maybe it's actually rotating about this contact point here. All right, so normal force in the case won't be making it rotate. What direction is gravity making it rotate? Counterclockwise, right? Let me do one more. So, all right, we are done with the normal force and gravity. Let's say I just pick a random point. I just pick a random point here, for example. Combination of gravity and normal force. What direction is it trying to rotate? Counterclockwise. So it almost doesn't matter, at least in this case, where I pick. The combination of these two is that it's going to try to make it spin counterclockwise. So that's where you run across the difficulty here. The forces that we have drawn so far is not enough. I have to introduce additional forces so that this static equilibrium condition holds. Okay, where can I find my forces which is going to make this rotate clockwise? And let's make it simple for me. Let's say this is going to be my center of rotation. So I want some force that will generate torque that's going to balance out this torque. Yeah, where the ladder is touching wall. I mean, you hopefully had this intuition already. The ladder is leaning on the wall. There's got to be a normal force from the wall. And well, this is why. There has to be normal force from the wall to balance out the torque due to gravity. So let's say there's a normal force from the wall. Okay, so with all these three forces combined, you can see that net torque can add up to 0, right? Now, I ask this question every single time. This is an iterative process. After I draw the force, I ask myself both questions again. Can net force be equal to 0? And can net torque be equal to 0? Net torque can be equal to 0. That was the whole point. Can net force be equal to 0? No. Okay. Why can net force be equal to 0? So in the vertical direction, do you have any problem with the vertical direction? No, right? So what's the problem with the horizontal direction right now? Yeah, you need some kind of force that's pushing it to the left, right? You have a force that's pushing it to right. Unless you have a leftward force, your net force, which is a vector quantity, won't be 0. So where do you think you can get a leftward force here?
I have a normal force from the ladder to the wall.
No, that force is on the wall, not on the ladder. I want a force on the ladder. Downward, not horizontal. Friction. Yeah. So in this example, it's actually important that the floor and the ladder has friction. So the last force unit here is the force of friction pushing it this way. So, so this is the picture that allows a static equilibrium condition to hold. And what you saw with the other example, when I push this ladder slightly, somehow things have shifted enough that it's causing this friction to not provide enough force and slide. So before we go into break, let me just change one thing here and see that friction matters. Let me change the property of this ladder, material property. It right now has friction of 0.2. Let's make it 0. But before I do that, let me pause the simulation. And I'm going to make it so that friction is now 0. So it's a frictionless thing between the ladder and the floor. And when I now run the simulation, now it slides. Because now there's no friction, so it must slide. Yeah. So, okay, welcome back. I think I have enough time to show you one example. This is actually my favorite example. I used to introduce this topic with this example until I had a simulation to play with. So, well, you know, this is what we are simulating, right? Ladder leaning on a wall. And, you know, you can confirm the simulation that when I move this slightly, it's at some different angle, this ladder can slide out. So I mark the position where it does not slide out so that I can put it at the same position again. Now, what I want to simulate here is the physically realistic situation where you have a ladder leaning on a wall and your carpenter or whoever is going to walk up on this ladder. So this is a practical question. Suppose you're painting your house. You lean the ladder against the wall. If you see that it doesn't slide, you might even see that you step on the ladder at the low height. Let me simulate that by taping my mess to the bottom of the ladder. The ladder is kind of heavy in this case. They are both about 200 grams. So you even step on the ladder, jump up and down a little bit and see that the ladder doesn't slide. And you feel like the ladder is secure, and you start walking up the ladder. Here's the question: is the ladder really secure, or are you in danger of ladder sliding out from under you? Let's try it. So I'm going to move this up maybe here and see what happens. Up somewhere, all right, here. I haven't actually tried this exact position, but I'm pretty sure it'll work the way I think. Okay, so you are at the top of the ladder. The ladder is in the same position it was in before. Now let's see if it slides. Oh, wait, it doesn't. Sometimes it works, sometimes it doesn't. Let me move the person up a little bit higher. I should have tried it at the exact position. Let me, all right, so to here, let me just double check, all right. I need to be closer to where it's going to slide, but not quite. All right, let me put the ladder. Okay, so you have almost reached the top. Let me try it here. I don't know. This is one of the reasons the simulation is easier. All right, so let go. Imagine the person were heavier. It's it's a function of what is the friction coefficient and all of that. Well, yeah, I should have tried it out before class. But okay, let's imagine the person is heavier. So that was 200 grams. This is now 500 grams. All right. So there are situations where the ladder seems secure, and it is secure. It's not always insecure when it seems secure. So I'm just trying to answer the question, well, is it always secure when it seems secure? So this is a situation where it seemed secure at the beginning, and now let's see. It is secure. Oh, okay, here it is. So ladder seemed secure at the beginning, around here. I'll try it again, move it down here, and see if it's actually secure at that position. But when you have walked up here, this is what you find with the ladder, that it slides out from under you. Let me put this, since it's a different method than what we initially tried out with, let me put this here. And just to confirm that at the lower position, the ladder was secure. But somehow it became insecure by the time you got to the top. So when you're at the bottom, it was actually pretty secure. In fact, it was so secure that you could pull it out here and it still wouldn't have slid. But somehow, in the process of you walking up here, ladder became less secure so that you slide it down. So that's the situation that we want to analyze. I think we actually have enough time. And if I don't waste too much time, I think we have enough time to actually finish this analysis. So this is the way you can state the question. In fact, this question is on your worksheet. It's the problem. It's problem 6 on your worksheet, or sorry, problem 7 on your worksheet. And there are other problems there which are good, but I don't quite have enough time to go over, so we probably will skip all the other problems. So this is the problem I call Carpenter ladder. And here's my wall and floor, and here's my ladder leaning on it. Let me give you some numbers so that we have something concrete to talk about. So what angle do you think is easy angle to work with? Any preferences on the angle? 60? Yeah, 60 is an easy angle. It's one of the special angles that I have a lot of numbers memorized for. So let's say this is 60 degrees. And the ladder has some mass m, small m. And the carpenter will have some mass m, capital M. And some other numbers that I would have to specify. Let's say that the ladder is length L. Good. And from what we saw with the simulation, I have to specify some friction coefficient here, right? Let's give it a number. What friction coefficient do you think is a reasonable friction coefficient? For a ladder which doesn't have a rubber foot, which will increase friction coefficient, but just like wood against the plastic floor. 0.3? Okay. Yeah, 0.3 seems good. So it doesn't really, yeah. I don't know, 1 is easier to work with, but 0.3 is fine. It's some number, right? In fact, okay, yeah, I have a little bit of an issue with the 0.3. In fact, this is so low that the ladder will actually start sliding right away. Can I? I can actually I can work with this, yeah. So, and because when the carpenter, let's do 0.5. So if this is 0.5, and when the carpenter's here, it'll all be fine. But what you will find is that as the carpenter walks up, when the carpenter reaches a particular position, call that X maximum, you'll find that the friction force is at the maximum, and if he steps one step farther, the whole thing will slide out from under him. Okay? So that's the question we are trying to answer or trying to analyze, and this is our question. What is this maximum position that the carpenter can step up to before he falls to his death? Yeah, it's a safety question, right? How? So by the way, that's one of the reasons when you are working with the ladders, you do have to be careful. Like something that can look secure at the bottom can be insecure as you walk up. So. Yeah, anyways, so let's see if we can actually do this analysis. I'm telling you that we have all the tools we need. Let's see if we can. Okay. So this is a standard strategy problem. As in we are going to do the force analysis steps like we have done with all the similar problems before. The only difference here is that now we are dealing with one new quantity that's kind of similar to force. That we are now dealing with a torque. And because we are dealing with the torque, when we draw free body diagram, let me draw it here. When we draw a free body diagram, we are going to be careful to be able to indicate the location of the force so that we have a value for this change difference of position. So the way I'm going to represent this ladder is as a long line so that I can indicate the positions of the locations where the forces are acting. So let me express the ladder as a long line that has the same length as the ladder. So I had to start identifying the forces. What are the forces on this ladder? Let me say free body diagram of ladder. What are the forces on the ladder? There's always gravity. So I'm going to interpret the word gravity to mean the ladder's own weight. Okay? And I will justify this again later, but I'm going to say the weight of the ladder is acting at the center of mass of the ladder, at the midpoint. So there's going to be gravity, mg pulling it down. Tika, what were you going to say?
The gravity of the person.
There's going to be there's going to be the weight of the carpenter. But that actually won't be on the ladder directly. It's more like a gravity pulls down the carpenter, and there's an interaction between the ladder and the carpenter. So it's actually some kind of normal force that's pushing it down. But let me simplify it and just label it as mg. Because if they're not accelerating, that's what it should be, right? So let me, so I guess I will label the position. So call the position x, max. And at this position is where the carpenter is touching the ladder, is where the force big mg will also be acting. Good? All right, this definitely doesn't look like a complete free body diagram. There's no way net force is equal to 0 or net torque is equal to 0. So there must be other forces. Yeah, there's going to be normal force pushing the ladder up from the ground. And as you look at this picture, you realize that the only point of contact with the ground is here. So, all right, so I'm going to have force pushing up here, normal force from, let me call it floor. All right, so this looks okay net force-wise. I can have downward forces equal to upward force. But as we looked at before, the net torque doesn't look like it can be 0. So what can I do to make a net torque 0 in this picture? Now, when I introduce, so friction force will be here, right? When I introduce friction force here, you will realize that one, it actually introduces two problems. One, friction force here, it will introduce a horizontal force that's not balanced out by anything. And here's actually the second and worst thing. Whichever direction the friction force is, it actually doesn't help with my net torque. Like, imagine this friction force. Does it allow my net torque to add up to 0? It still looks all counterclockwise, right? And if it's the other way, it's still the same thing.
Which is why you apply the force from the wall.
Yeah, that's why we need a normal force from the wall. And I hope it makes intuitive sense that the ladder is leaning on the wall. It is contacting the wall. So there should be some force from the wall, which we so far have not drawn. So, this is going to be somewhat complex free body diagram. That's why I want to go in order. I want to draw in these forces as they are needed. So the next force we need to make the net torque add up to 0 is that there has to be normal force from the wall, pushing it that way. Now, looking at this free body diagram, I go through these two checks again. Is net force equal to 0? Is net torque equal to 0? This should be fine. That was our whole goal for the previous step. Is net force equal to 0? No, so what can we do to fix that? Yeah, this is the point at which I introduce friction at this point of contact and say that friction is pushing it to the left to balance out this force. Now, let me explain one simplification. So I'm treating the wall as though the wall is frictionless. because there could be upward or downward friction force, but I'm kind of ignoring it to make the problem as simple as possible. Okay? Because with these 1, 2, 3, 4, 5 forces that we have drawn, it is possible to set up the equations and see answer this question of what is the highest position that the carpenter can climb up to before he falls to his death.
You said there could be a downward frictional force?
So, with the wall, if there's a friction coefficient with the wall, then you can imagine there being a friction upward or downward. So that would either add to or subtract from this force. So, it can physically be there, but for the purpose of this problem solving, I'm going to simplify it as much as we can. And for me, that means I'm going to make whatever can be frictionless, make it frictionless. Okay? For the ground, it's impossible for that to be frictionless. If it was, it'll slide as you saw before. Okay, so this is our complete free body diagram. So let me go through some of the steps that you are already familiar with. What you are already familiar with is, so this is step number 1. Step number 2, define coordinate axis. My acceleration is 0, so I have some degree of freedom. I'm going to define my coordinate axis the same way, the usual way. Like I'm not going to tilt it or anything. That seems, insane. So I'm just going to define it the usual way. And okay. Third step, break down forces into components. Well, they are already in x or y direction. That's why I picked this axis. So let me go to step number 4 and write down Newton's second law equations. And after that, I will describe what additional things you have to do, because now we are handling torque as well as force. So we say net force. So how many equations do I write down? 2? Yeah, 1 object, 2 axes. So it'll be net force in the x direction and net force in the y direction. So we say net force in the x direction, normal force from wall minus the friction force is equal to 0, zero acceleration. The net force in the y direction, that would be the 2 gravity and the normal force. So small mg, wait, downward is negative. So let me say normal force from floor minus small mg minus big mg is equal to 0. Okay? So this is what we are used to doing so far. And when you look at this, you will see that this gives you no way of answering this question because, well, x doesn't occur there. And this would be another reason you have to consider the torque. Because as the carpenter moves up, his force doesn't change. The only thing that's changing is the torque due to where the distance is. So we are going to have to write down this equation. We are going to have to write down what is net torque. And whenever you are considering torque, this is the very first thing you need to do. You have to define your center of rotation. Okay? I'm seeing that I'm kind of running out of time, so let me do this quickly. I'm just going to define it myself and explain quickly the reason why. So I'm going to define my center of rotation to be located here. So here, I'm going to say my center of rotation is here. And this is really my reason why. I'm looking ahead to calculating the torque, right? Torque for any force becomes very simple if I say that I can say delta x is equal to 0. If I locate my center of rotation here, then normal force provides 0 torque, and the friction force provides 0 torque. So that makes my life easier. That's why I'm picking this as my center of rotation. Good? And I only have to worry about the counterclockwise torque from the 2 gravitational force and clockwise torque from the wall. Okay? So let me write that down. I'm going to make a counterclockwise positive. That's actually the usual convention. So I'll say counterclockwise is positive. Okay, so net torque is, all right, plus mg times the displacement, x, times the angle. So here the angle that I want to look at is, so this is the angle theta that I need to look at. The angle that we are given was 60 degrees. So let me just write in the angle. So it'll be sine of 30 degrees. So mg sine of 30 degrees plus small mg times, here this time it's not x. This distance will be the length divided by 2. Okay? So L over 2 times sine of 30 degrees again, plus the force is normal force from the wall, and wall, times, what is the displacement? L, the entire length of the ladder, times. So here the angle theta would be this angle here. How much is this angle? Yeah, 60 degrees. So let me write that down as sine of 60 degrees. And net torque must also be equal to 0 to hold static equilibrium condition. Okay. Let me just quickly demonstrate that this is solvable. As in, we have 1, 2, 3 equations, and I'm going to count 3 unknowns. We have normal force from the wall. We have friction. We have normal force from the floor. And we have x. Wait, that's 4 unknowns. I need one more equation. Any guesses? Asia? Yeah. Static friction condition, meaning this friction is less than or equal to coefficient of friction times the normal force from floor. So this is my 4th equation that does not introduce any more unknowns. Right? So, go through this. We can go through this to solve for x. In the interest of time, I'll just do it quickly myself, but I highly recommend that you try it out. It's not difficult algebra, but it's now getting now it's developing interesting complexity. So let me do it this way. I'm going to try to put everything into this expression here. So I'm going to solve this for n floor. So let me say normal force from floor is equal to this, so small m plus big M times g. I'm going to plug this in here. And for the left-hand side, I need the expression for friction, which from equation 1 will be the normal force from the wall, which is another unknown. So I need to go to this equation here, solve this for normal force from the wall. Right? Let me make my life a little bit easy and replace these with the values that I know they are. Sine of 30 degrees is 1/2. Sine of 60 degrees is √3/2. So I'll just deal with the numeric numbers that way. When I solve this for normal force from the wall, this is what I get. Solving for normal force from the wall. Wait. Sorry, this should have been minus sign, because or plus. There should be a minus sign here. So I'll move this over to the other side, divided by L √3/2. So normal force from the wall will become so 2 times over L √3. That's the factor that I moved over that I multiplied through to get rid of it on the right-hand side, times everything that's left on the left-hand side. So that'll be big M times G, X times 1/2 plus small m times G, L/2 times 1/2. I'm just copying over everything that's here. So things cancel out. These 2 cancels out these. Well, L doesn't really cancel out. So let me just write out the final version this way. I'm going to factor out G. So G times big M X over L. In fact, let me write that G over √3. So mx over L plus, this cell cancels that L out. So it's small m over 2. Good? Yeah, so put all these, or I guess put n floor and n wall into this expression. this is what you end up with. That, let me write this in purple. So the friction force, that's the normal force from the wall. G over root 3, big M x over L plus small m over 2. That's the expression for friction says that's less than or equal to all of this. Mu of S times normal force from the floor. Small m plus big M, small m plus big M times G. You see that once all of that's written out, some of the things cancel out, as you might expect. G cancels out, so it doesn't matter what gravitational acceleration is. And the rest is a matter of doing the careful algebra to leave x by itself. So I would multiply both sides by root 3 so that I don't have this root 3 here anymore. And then I would add both sides by m over 2 to move this over to the other side. Sorry, subtract both sides by m over 2. It's minus m over 2. So get rid of this here. And now I multiply both sides by L over M. Right? So take this, multiply both sides by L over big M. Then now I'm left with just x. Good. Let me write down the cleaned up version. The cleaned up version is that x is less than or equal to the L over M times friction coefficient mu s times small m plus big M times root 3 minus small m over 2. Good. I guess we can simplify one. Sorry. So here's one way we can actually make this simpler. Because it's a complicated expression. I hate to leave it there because you are just staring at the complicated expression without having any intuition for that. So we could say, well, what does it look like if the ladder was very, very light? So ladder has 0 mass. Then this would be 0, and this would be 0, and the ratio you get here would be less than or equal to mu s times m's cancel out, so L times square root of 3. Mu over s was 0.5, so he can go all the way up to about root 3. So the distance that he can go up to would be root 3 over 2 L. So before he goes to the highest point on the ladder, it'll start to slip. Good. No questions? Okay. I want you to bring up one more example that I kind of want you to bring up last class, but I didn't get to it. So let me bring that up. Let's see. Do I have? Okay, I think I still have that example from last time. Okay, so this is the thing with the thing that I wanted to talk about. So it's nothing special. Oops. All right, that's better. So it's not a very remarkable setup. All this is, it's something that will provide a known force that I'll specify soon. And the block has a bit of a special property. When you look at the material property, it has infinite friction coefficient. Meaning, so as I push it, it won't slide sideways. Because, if it had, so if it was frictionless, you can imagine what would happen as I apply some small amount of force. As I start applying some small amount of force, it'll begin to slide, no matter how small that force is, right? So let me increase the friction back. So when it has infinite friction, essentially the static friction has no limit. It can provide whatever necessary horizontal force to keep it from sliding. So here's the question I want you to ask all of you. In terms of, checking your intuition and having you build the correct picture of how things move, especially once you start including torque and the things we were talking about last time. So what do you think will happen as I increase this thrust? So right now it's not a lot of thrust. It's less than a Newton. So let's say I increase it up to a Newton. Nothing happens. Let's say I increase it up to 10 newtons. Nothing happens. Let's say I increase it up to 50 newtons. Now, here's the question. Do you think that will continue to happen? Or is there some point at which I'm applying large enough force that something other than static equilibrium will happen? If you're trying to think of, rely on your intuition, this is what I want you to think of. Imagine this block, and imagine that there's something that's providing enough horizontal force so that it won't slide. As in, well, I could actually do that by putting my finger here. Then, this finger will stop. It'll provide whatever necessary horizontal force so that this won't slide. Now, imagine I'm pushing this from side. Is it the case that no matter how much force I push it with, it won't move? Or is there at some point some kind of motion will happen? So what kind of motion do you expect to see? Yeah, you will expect that it'll tip over, right? And you see the same thing happening here. Let me keep increasing the force. And at some point, yeah, it starts to tip over. So what I want you to have the tool to analyze this with is, well, why does it tip over? Can you draw a free body diagram that will explain why it tips over? As you think about it for a minute or two, let me draw the picture for a free body diagram. So anyone have an answer why it tips over? Or let's put it this way. I can look at the material property of this box. Let's see, material. It's around, let's make the number easy for us, actually. Let me make the number 10 kilograms. So it's a box of mass 10 kilograms. And I want to predict at application of how much force would it tip over. So, as I increase thrust from 0 to if I go up to 50 newtons, will it tip over? Well, not quite yet. Okay, at what force would it begin to tip over? 100? Maybe. Let's try that. That was close to the number we had before. So let's see. Almost. Let me try going a tad bit more. 105. Yeah, 100 probably was it. So Abdi, why did you guess 100?
Because it's equal to 10.
Okay. If that's your reasoning, let me change the geometry slightly. Let me bring the force back down to 0. And instead of I pushing here, I'm going to push it up here at the very top. The force that's required to get it to tip it over, do you think it'll be greater now or smaller now?
Small.
Yeah, that's what your intuition says, right? It's easier to tip this over when I push it at the top than in the middle. Okay, how much smaller? By half? Okay, so you do have, most of you do have good intuition for, when it will tip over. Now, what I want you to have is a tool for predicting what that will be. The rigorous tool to actually figure that out with. So that's going to be free body. So you guys have good intuition, which is good. What intuition is knowing the correct answer without doing all the work. Now, that won't give you full credit on the exam, but knowing the correct answer does, it cuts down on a lot of blind alleys and waste the time you could be wasting. So intuition is great to have. If you don't have it, start working on it now. If you have it, continue nurturing it. So we analyze the forces the same way as before. This time what we are going to do is we are going to draw a free body diagram in a way that first explains why when the force was less, that it didn't tip over as I was applying some amount of force, that it didn't tip over. And why at a particular value it begins to tip over. So let me draw forces on these bodies, because right now I'm not sure exactly what kind of simplification is leading to the result. So I drew the whole object so that I can correctly indicate where the forces are. So there's going to be gravity on this body. At which point on the body would you say that this is where the gravity acts? Center of mass, so if it's uniform, somewhere in the geometric center of the object. So I will draw gravity this way. So this is going to be mg. And the normal, usually I draw the normal force next, but this time let me actually draw the applied force first. So let me draw so I'm applying the force at this corner, right? So I am applying a force at this point, moving to the right. So this is my applied force. Okay, there's one force that's not shown on this free body diagram yet. Oh, sorry, two forces that's not drawn in this free body diagram yet. Friction is the one that actually is the easiest to draw. So let me draw friction next. I'm actually going slightly different order than what I usually do. So friction will be somewhere along this contact, and technically it's over this entire surface. But let me pretend that it's at a single point, so I'm just going to average all those positions and say friction, it's almost as though friction is at this point. And say friction acts this way. All right?
Normal force?
Yeah, so the normal force is the one that I want to draw with care. Yep. So normal force is needed for two reasons. One, I need the net force, I need this. I need net force to be equal to 0. Right? That's one of the reasons I need it. But let me have you consider this. Where should I draw normal force? So it'll be somewhere on the bottom, but will it be at the center, like with the friction? Or will it matter where the normal force is drawn?
I think it would be on the bottom right.
Maybe the bottom right side. Yeah, so if you are thinking that already, then that's a great intuition. And you might even be thinking when it tips over is when, yeah. So let me give you the reasoning for this, if in case you don't know the answer. Question, comment? No, in case you don't know the answer, or you know the answer, but you are not sure why that's the correct answer. So, so it comes down to the requirement that net torque has to be equal to 0 also for static equilibrium. So here, I want to calculate the net torque. Now, the moment I say the word torque, what you have to think about it is, what is the center of rotation? So, right now it's not rotating at all, right? It's at static equilibrium. But you have to still define a center of rotation so that you can actually calculate the torque and see. It's impossible to calculate torque without center of rotation because, torque was force times some distance from center of rotation. From center of rotation times sine theta. So if you don't have center of rotation defined, then your torque is undefined. You have no way of calculating it. So I have to define a center of rotation. We'll talk more about choice of center of rotation later today's class. But this time, I'm just going to pick this as my center of rotation, as a sort of natural choice. Because when it does start to rotate, when you increase this thrust, and when it does start to rotate, well, it rotates about that point that I picked as a center of rotation, right? So I'm just picking a reasonable point as center of rotation. I'm not trying to be fancy and this time. So this is my center of rotation. So this is where I want you to look at these forces and see what kind of torque they are each generating. What kind of torque is friction generating? Does the friction force look like it's trying to make this object rotate about this point? Really? No, right?
It's resisting.
But I mean, yeah, friction is resisting this, but I'm just looking at friction. When you're just looking at friction, or you can fall back on this definition that we wrote down. What is sine theta for friction? 0 or 180, whichever. So, here it's actually 0. So it's 0 degrees, so sine of 0 degrees is 0. So friction doesn't cause any torque. And it hopefully matches with your intuition when you just look at this picture. This is the point about which we are trying to rotate, and friction is going radially outward. It's not trying to cause any rotation. So the torque due to friction is 0. What about torque due to gravity? Is it clockwise or counterclockwise? Yeah, looking at this point, you can sort of see that it's counterclockwise. Imagine a bar that's here, and imagine you're pulling down this way. It's going to rotate counterclockwise. What about apply the force? Yeah, clockwise. So you can imagine that when the torque due to gravity and torque due to apply the force. When they balance out, then it'll be zero torque, and there doesn't need to be any torque due to normal force. Now, when I wasn't applying this force at all, as in when it was this picture, let me change this first. When it was back in this picture, why isn't this rotating if gravity is providing counterclockwise torque? Why is this not rotating? It's balanced out by torque due to normal force. So if I don't have this applied force at all, where I would have drawn the normal force, I would have drawn it here, pointed up. So that would have been the normal force, and both the gravity and normal force will add up to zero force, and they would add up to zero torque. Now, what happens to this normal force as I start to apply the force and start to balance out some of this torque due to gravity? So, the point where I apply the normal force will have to move. Which direction does it move? Yeah, it'll begin to move to right, because as I increase this applied force, the normal force has to provide less and less torque. So, normal force is similar to friction. It's over the entire surface, but instead of being uniformly distributed, its balance will change. There will be more weight on one side than the other. So that's what this is representing. There's more weight on this side than this side. So the moment before this box tips over, where should I imagine normal forces apply? Right at the corner. Right at the corner is where the normal force is applying. And so here is where normal force is providing zero torque, because, well, it doesn't need to. The applied force provides all the torque needed to counteract the gravity. And the moment the force I apply goes over that is when it tips over, because the torque due to normal force can go only down to zero. It can't go negative. Yeah? So this is a pretty common situation, which is why a lot of you do have good intuition. But actually analyzing it, that's a new way of thinking about it, because so far you haven't had to worry about where is normal force on. Well, this is a common everyday example where you do have to start worrying about it. All this discussion of static equilibrium, it's been built up to rotation. So what I really want to go into today is rotation. So we are going to have to talk about rotation the same way we talked about motion. Oh, I keep bringing out this bicycle wheel because I can use this to illustrate the quantities we are talking about in rotation. So right now, this bicycle wheel is stable. It hasn't rotated or anything. Now, a moment later, has this bicycle wheel rotated? Yes? Did it move? How do you know? You look at this tape, right? It used to be on the vertical spokes, and a little bit later, it's on the horizontal spokes. Well, it must have moved. So, as a comparison, that's how we start looking at motion. So when we are looking at motion, I think this is like one of the first things I said on the first day. We look at position of an object, and the position of the object, unless we are talking about boring things like equilibrium, we are talking about where the position moves. So that at some later time, it's at some different position. So we are going to have a similar parameter for rotation. So instead of position, we are going to have an angular position. Angular position, which I guess we can mark it with the letter theta, which is the common letter you use to measure angles. So let me go over some of the peculiarities here. So let's say let me turn it around. Let's say the angular position you see right now for these tapes is zero whatever. What is the angular position for the tapes right now? Pi over 2 in radians, or 90 degrees. So is it plus or minus? A lot of you say plus. Yeah, you might be importing your sense of direction from your geometry class, which is fine. In your geometry class, counterclockwise was positive. Starting from positive x-axis, going over to y-axis was positive. Okay, so this is pi, right? This is, okay. Now, what's the total change in angular position? Any other answers?
2 pi.
Yeah, 0 or 2 pi. Now, if you just saw this position just out of the blue, you wouldn't know which one. But imagine this. Let's say this was the initial angular position, and over time, you observe these tapes moving this way. Round, round. And somebody asks you for the angular displacement of these tapes. So once again, I guess you could give multiple answers, but the most correct answer is 4 pi. So that's one of the peculiarities with the angles, right? That it repeats every 2 pi. So you could choose to take modulo 2 pi, as in you take the thing, divide out 2 pi, and take whatever the remainder, and say that's your angular position. And if you're talking about the position at a fixed time, that would make sense. But for the mathematical operations that we are going to do, you might want to keep the history of the thing in mind. Because maybe this angular position that I'm relating to, maybe that will be related to how far this rolls. So if I'm trying to measure, how far is this wheel rolling as it rolls without slipping over some surface. And I want you to imagine it's still rolling without slipping. And if I ask you how far did it roll, the answer is going to matter. Is this 0 or 2 pi? Or as it rolls more, the answer is going to depend on, the answer for the distance is going to depend on, is this 0, 2 pi, or 4 pi? And what I'm telling you is the answer of 4 pi will never be wrong, whereas answer of 0 or 2 pi could be wrong sometimes. It's some peculiarity. We don't deal with it too much, so I want to highlight it, but not spend too much time. One last question. I have actually 2 different tapes on this wheel. Do they have the same angular position or different angular position? Okay, they have different. Ali, you said same. Why did you say same?
Because they are on the same line.
Yeah, they're on the same line. Yeah. As in, what would you say is the angular position of the small tape? 0. Okay, 0. What's the angular position of both of the tapes? Pi over 2, both of them, right? Yeah, so their positions are different, but their angular position is the same. So, and we'll talk a little bit more about the relationship between position and angular position. But the starting point is angular position. It's, let me start writing it from the beginning. So it's, you could say this is defined in analogy, or in comparison, or analogy is the word I prefer the most. Analogy to the position x. And this angle theta, it can be a function of time. Just like in most interesting cases, position was also a function of time. Yeah? So remind me, when we are dealing with the motion, what did we do with the position once we defined it? Did we define anything else using that definition of position? Yeah, we defined the velocity, right? And then we define the acceleration. So we are going to define similar quantities for rotation. We have angular position. So now we are going to have angular velocity. And we are going to have angular acceleration. And when I start writing down the relationships, I hope it starts to look familiar. As in angular velocity, I would define that. So omega is the symbol I use. I'll talk about the symbols in a bit. So angular velocity, we would define that as the time derivative, or rate of change of the angular position. And angular acceleration, we would define that as rate of change of angular velocity. And I'll talk about the letters we are using in a bit. And whenever you feel confused or whatever, the picture that I want you to come back to is the linear motion. because a lot of people have good intuition for linear motion, even when you can't do kinematics problems, but you have good intuition still. You see a lot of things moving linearly. So the angular position is analogous to position. Angular velocity is analogous to the velocity that you have seen before. And angular acceleration is analogous to acceleration that you have seen before. How many here remember what analogy means? I don't know if, how many here had to take SAT? But they took analogy out of SATs now, right? That happened many years ago. So it doesn't work. Where else would the typical student see analogy? It's like, what's an example of analogy? But what it is it's a relationship. So if you have a relationship between two things, that's similar to relationship between other two things. You could say a driver of a car is to, the relationship between driver of a car to the car is like the pilot of airplane to the airplane. Now those are completely different things, but those relationships are similar. And that's really what we mean by analogy here. Angle is nothing like a position. But when you look at these relationships here, remember how we defined velocity. We defined it as rate of change of position, and we defined the acceleration as rate of change of velocity. The new relationships that we have defined here, they follow the pattern that you saw before. That's really what we mean that they are in analogy, as in they are comparable. So velocity is to position, the same way angular velocity is to angular position. Yeah. So one aspect of that is that even though we want to keep referring to these old quantities that we have defined, we want to make sure that these two things, they are not the same. The angular velocity is not the same as velocity. So that's why we have to assign different letters to denote angular velocity. And we have to assign different letter to denote angular acceleration that's distinct from the letter for acceleration. So I think most of you actually saw this Greek letter. So by convention, all the rotational quantities are given Greek letters for some reason. You saw that with the torque, we use the Greek letter tau. So for position, we use theta for some reason. I think you guys actually have seen this letter before. Omega, right? And I just want you to be careful with omega. My omega, you have no excuse for confusing my omega with my W. I know some people write them in a way that they're confusing. I never do. My omega bottom is always rounded. My W bottom is never rounded. So W and omega are completely different. They're nothing like each other. Okay? And I think alpha is pretty distinguishable from A. No A I ever write has this upper half tail. So, yeah. So these are the basic quantities we start out with when we are discussing angular motion or rotation. So when you have this, right now, what would you say is constant in the motion of this wheel?
With no friction.
Yeah, ignoring friction.
Velocity. Or angular velocity.
Yeah, angular velocity is constant. Its angular position is constantly changing. It's going from 0 to 2 pi, and then another 2 pi, another 2 pi, like once every second or so. So angular velocity is one thing that's constant because it seems to be rotating at the same rate. Now, would you say angular acceleration is constant here?
Yes.
Yeah, constant at 0 value. Now, what would the motion with the angular acceleration at a constant non-zero value look like?
The wheel would just increase in speed.
Yeah, so I think I find it hard to do it with the bicycle wheel, but I can do it with this turntable. And I probably should set this up at some point today. So let me do that now. All right. Good enough. So this is the way I can get constant angular acceleration. I can use friction. So I can, start moving my hand over it. at some constant normal force. So the amount of kinetic friction is the same. So as I keep moving, it angularly accelerates. I guess it's kind of hard to see on that screen, especially without a marker to use as a guide. So let me put down a blue tape as a kind of a marker. So let me put down a blue tape in one part here. And I'll try to avoid the blue tape as I angularly accelerate it. So a motion with a constant, let me do it in a way that it's going in the positive direction as seen by you. So a motion with a constant angular acceleration, constant positive angular acceleration, the way we normally define it, might look something like this. So at some point, okay, I can't rotate it anymore. But good. And all of this matches with your intuition about linear motion. Like, a linear motion with a constant acceleration would start out slow, but over time it'll reach higher velocity. And it's the same thing here. So I guess I will tell you one thing that may be a relief or maybe not. So we're kind of going to skip rotational kinematics. But let me point out this much. So you guys had kinematics formulas, right? You had a linear, so we didn't call it linear because everything was a linear then. But you had a linear, constant acceleration, kinematics formulas. Everyone here knows what I'm talking about? Yes? No? The velocity as a function of time is initial velocity plus at. Position as a function of time is initial position plus v naught t plus 1/2 at squared, right? And to cap this off, the v squared formula, v final squared is equal to v initial squared plus 2a delta x. Like, all of this looks familiar, or you've seen this before? What I'm telling you is that without explicitly driving them, there's an analogous version of this formula for rotation. So I could just, from knowing all of this, I can go through the derivation all over again. It'll be the exact same derivation with the symbols switched out. But when I do, what you would get is rotation, so rotational, constant angular acceleration kinematics formula. And from knowing this, I can write this down, not even from memory. I'm essentially taking this expression, and wherever I see v, I'm substituting in omega. So I can say, well, so angular velocity as a function of time is equal to some initial plus, I have to replace a with the angular acceleration. Angular acceleration times time. Time is the same for both of them. And the same thing for position. So theta as a function of time is equal to initial position plus initial angular velocity times time plus 1/2 angular acceleration times time squared. Or the v squared formula in the rotational version of them. So omega final squared is equal to omega initial squared plus 2 times angular acceleration times change of angle. Is it clear how I'm writing down all these formulas without having anything to refer to other than this? Yeah. So I'm pointing this out as a reminder that all the things you learned in kinematics, in translational motion, they still apply. All the method, that's why it's worth going back and reviewing if you didn't feel like you did so well in kinematics, because whatever you learned then will be useful for what we are covering now. As you are doing rotation, it'll help you to go back and review anything that you didn't get the first time around, because sometimes it just takes time for things to sink in. Yeah, so this is the start of the discussion of rotation by being able to describe, where things are. So I think this might be one of the homework questions, or I might be confusing with the physics 10. So call this 100 gram mass Bob, and call this Alice, and call this 500 gram mass Bob. Then these two are at the same angular position, as you can see on the screen. right? And actually, let me make them the same mass so that you can kind of see the difference. The only two masses I have the same ones over 200 grams. So should I write their names? Okay. So the one that's on the inside is Alice for A, and one that's on the outside is Bob, or B for Bob. All right. So they're at the same angular position, right? Good. And as they move around, they remain at the same angular position. But if I start spinning it faster, something different happens with them. Let me move this away. I don't want to break anything. So as this starts to spin faster and faster, Bob slides out while Alice doesn't. Why? Like, what? I mean, I thought they were at the same angular position. So what was the difference between Bob and Alice? That Bob slides up, but Alice doesn't. Yeah, so Bob is actually moving faster, right? You can see that the linear velocity of Bob is faster. So when you look at this, so you can talk about the angular velocity, but sometimes you will want to talk about the velocity. So you should know how they are related. So let me call it this way. Relationship between the rotational quantities, angle, angular velocity, angular acceleration, and the translational quantities, linear motion, position, velocity, and acceleration. And if I'm being perfectly clear, as in non-ambiguous, that's usually what I mean when I say clear, anyways. I should clarify that I mean these to be tangential quantities. As in when I talk about x, I don't really mean x in the sense of, moving from here. So, I sort of put them along the x-axis, right? When I say x, I don't mean position along your imaginary x-axis. That's not what I mean. When I talk about x, I'm talking about the motion along the circle, along the periphery of circle, or what we call tangential direction. So what I want to briefly go over is the relationship between the angular quantities and the tangential motion-related quantities. Yeah? So let's start out with the velocity. I think that's the one that comes up most often, so maybe it's the most useful. So let's say I know angular velocity somehow. It's given to me, I calculated it, I measured it. Somehow I know omega. And from omega, I want to be able to calculate what velocity or tangential velocity is. What do I need? Is omega by itself sufficient, or do I need to know something else? So as you are trying to figure out the tangential velocity, the one additional parameter you need to know is the distance from the center of rotation. Let me call that r. And that's kind of why we use the word radius often for that, because we are imagining a circle that this is moving in the path of, and we are imagining radius of that imaginary circle. So let me set aside this r. So does anybody in here know, using this r and omega, what the expression for tangential velocity should be? Or let me go back to the one example for position. Maybe it's easier for position because you can visualize it better. So let's say I have a change in angular position. And from knowing the change in angular position, I want to be able to get to some kind of change in the position, but it's not delta x in a straight line. It's delta x along the circumference of the circle. So let me draw a picture to help us imagine what this looks like. So let me draw this circle here. This is my circle of radius r. And yes, someone was saying arc length, right? So what this delta x is, it is arc length. So it comes down to the question of, all right, so you know the radius r, and let's say for this particular arc, you know the angle here, delta theta. How do you express this arc length? One person has Abdi, please.
R theta, R delta.
Yeah, this arc length is equal to, trying to color code it, R times theta. Theta I'm using, oh wait, I mixed up my colors. Okay, so Abdi, how do you remember this formula? Why is the arc length R times delta theta?
Because the circumference is towards the,
Well, 2 pi r?
2 pi r.
Yeah, so, okay. My question was actually kind of backward. So the proper way to remember this is remember how we defined the angle in the first place. It goes back to the definition of radian that we spent some class time on. Angle itself is actually defined as the arc length divided by, so if I call this the arc length, delta x, then angle itself is actually defined. The definition of angle is the arc length divided by the radius. That's how radian is defined as angle. So once you know this, then the rest of what I'm asking for here is simple matter of doing a little bit of algebra. Solve this for delta x instead of delta theta. Then you get for arc length that's equal to the radius of the circle that you're imagining times the angle, delta theta. Okay. A tangential velocity, that's a very simple formula. That's just the radius times the angular velocity. Just recall back to this, and that's just the relationship between tangential quantity and angular quantity. That is the relationship between angular quantity and the tangential or linear quantity. And this continues on from position, velocity, and acceleration. You can look at it either the same relationship carrying over for different cases, or you can look at it this way, taking this expression and just taking derivatives. When you take the first two derivatives, you get the velocity for left-hand side, and you get angular velocity for right-hand side from these relationships here, And then if you take another derivative, then here you get angular acceleration, which can be used to express the acceleration or tangential acceleration. So by the way, this is another thing to point out. This tangential acceleration we are talking about, it has nothing absolutely to do with centripetal acceleration. Centripetal acceleration was a radial acceleration. Now that we are talking about rotation in full, it's especially important that you don't mix up tangential with radial. It's two different directions. So tangential acceleration follows the same relationship here. This is equal to radius times angular acceleration. Okay. So these are all very simple relationships. And it's simple because it's coming from a simple definition. But once again, the thing with these simple things is that if you miss this fundamental step, none of this looks simple to you. It's just another jumble of formulas that you are mixing up with your centripetal acceleration formula and a bunch of other formulas. It cannot be that way. This is based on definition. And I replace these almost at the level of definition. Okay, so this is sort of the introduction of the language that we'll be using. So, when we talked about motion, kinematics, that was the language that we used to talk about the things that we were actually interested in, forces. Then from that we talked about work, energy, momentum. Work, energy, momentum, and I guess impulse. So when we are dealing with the rotation, we are essentially retracing those steps again. So this is the language we'll use. And whenever we want to translate between what we did before, this side, to what we are doing now, then this is our translation table from the linear quantities to the angular quantities. So, and we are going to use this language to discuss the dynamics that we are interested in rotation. One of them will be torque. We talked about that last week. And we are going to bring up energy in terms of rotational kinetic energy. And we are going to bring up something called angular momentum. That will be like the Thursday before your exam. So